Welcome to section 8.7. This is where we're going to start getting an introduction to Taylor polynomials, Maclaurin polynomials, approximations, and so forth. Now, just as a little disclaimer, this is how we're going to cover it in BC Calculus, which does cover Calc 2 information, but we are not going to be able to cover it in the depth that Calc 2 is going to need. So if you're in Calc 2 and you're looking at this, please note that you are going to need to go deeper than we are going to go in this BC class. Now, a Taylor polynomial, not to read to you, but I'm going to be reading to you for the next two slides. A Taylor polynomial is used to approximate other elementary functions, like the natural log of x, e to the x, sine of x, and cosine of x. So this is what they did in the olden days. No, not when I was a little girl, even older. I know, weird. But this is what we did before we had the calculator. These are actually, this program, or the Taylor polynomial, is how they came up with the program to find your sine, cosine, natural log, your e to the x. So this approximation is the root of your calculator. Now, to find a polynomial, okay, we're going to call it p of x, that approximates another function, which we'll call f of x. So f of x is this guy, the natural log of x, e to the x, sine of x, cosine of x, the function that's going to be approximated. Okay, well, to find a good approximation, they need to have a point in common. That point in common they'll call x equals c. C for common. Okay, so that's the point where your approximated function and your original function equal. Okay, now the approximating polynomial called p of x is said to be expanded about c or centered at c, that point that they have in common. And that c value is usually going to be given to us. Okay, now there are an infinite number of functions that we can use to approximate the original f of x, but we want to make sure that it's a good approximation. Okay, so in order to be a good approximation, we need to use other parameters or other factors in common. Well, we're in calculus, so derivatives seem like a good thing to do. Now remember, the derivative is the slope of the tangent line, so that first derivative, okay, that's going to give us a linear approximation. And we all know that a linear approximation is pretty good. It's an easy approximation, it's an easy function to use, but it's not as accurate as you move away from that point they have in common. So they will be really good at C, but a little bit farther to the right, a little bit farther to the left, and that approximation is not good. So to prove the approximation, we impose yet another requirement. We're looking at the second derivative. This is going to give you a polynomial, and they call it p sub 2 because you use the second derivative, p sub 1 because you use the first derivative. It actually has the same increasing and decreasing behavior and the same concavity, so it's making a better approximation as we move a little bit further away from that c. So what we're going to end up with is a Taylor polynomial, okay, p for polynomial. That's approximation centered around that common value, that point they have in common, c. And look at what we end up with. Now, we discussed the fact that using the first derivative was a decent approximation. Using the second derivative was better. Using the third derivative, oh, better yet. Fourth derivative, fifth derivative, sixth derivative. The more derivatives you use, the higher that degree polynomial, the better your approximation is going to be. So this is our formula for the nth Taylor polynomial for f of x, centered or expanded about x equals c. Okay, so they'll call it the nth degree Taylor polynomial. Now, they're going to tell us what c is going to equal most of the time, and they're usually going to tell us what degree they would like us to take it to. Now, when you look at this formula, it looks kind of scary until you break it down. Okay, this is the original function's value at that common point, the point that they share, plus the first derivative at that c value. Okay, so first derivative, divide it by 1 factorial, multiply it by x minus c to the 1 power. So this is all that first derivative. We're going to add it to, here comes the 2's. Second derivative's value at c, 2 factorial, x minus c to the 2nd power. Okay, if we were to do that third term, we would have, or that third degree, we would have the third derivative's value at c over 3 factorial, x minus c to the 3rd power. Okay, so you've got your first derivative, you have all the 1's. The second derivative, you have all the 2's. Third derivative, you have all the 3's, etc. And remember, once you get up past the third derivative, they start putting parentheses and your number so that you don't think it's to the 4th power, to the 5th power. You know it's derivative because it has the parentheses. So n factorial, x minus c to the nth power. We have a Maclaurin polynomial, which is simply a Taylor polynomial where c is equal to 0. Okay, so that c is equal to 0. But notice first derivative, 1 factorial, x minus 0, or just x to the 1 power. Second derivative, 2 factorial, x squared. Third derivative, 3 factorial, x to the 3rd, etc. Now, I don't know why they do this. It irritates the you-know-what out of me, but they have a special name for a Taylor polynomial when c is equal to 0, so I don't know why you wouldn't use it. But sometimes they'll call it the Maclaurin polynomial. Sometimes they'll call it the Taylor polynomial centered at c equals 0. Okay, so if you have a special name for it, I don't know why you wouldn't use it, but you know how they can be kind of crazy. All right, so here's the problem that they give us. I've got it all typed out for us so that we can just kind of talk through it. Now, they want us to find the 4th degree Taylor polynomial for f of x equals natural log of x about x equals 1. So that is our c value right there. So c is 1. Well, to find a 4th degree, we'll need the 4th derivative. So I start off with f of x is the natural log of x. I find the first derivative, which is 1 over x. I find the second derivative, which is negative 1 over x squared. The third derivative, 2 over x to the 3rd. The 4th derivative, see that notation, is negative 6 over x to the 4th. Okay, so I need that 4th derivative. Okay, now remember, these top values right here are the derivative's value at c. So I take my original function and I put 1 in for all the x's. So I actually have the natural log of 1, which is 0. Here I put the 1 in for the x, so I have 1 over 1, which is 1. Here I put that 1 in for the x, so I have negative 1 over 1 squared, which is negative 1. I put the 1 in here, so I get 2. I put the 1 in, I get negative 6. So these are the values that go on top. So when I go to find that 4th degree Taylor polynomial, I have f of c, which is f of 1, which is 0. And then I have the derivative's value at 1, which is 1. So basically I have my f of 1 plus I have my derivative at 1 over 1 factorial x minus 1 to the 1 power. Okay, plus I've got my f double prime of 1 over 2 factorial x minus 1 squared, and so forth. Okay, so this polynomial right here is my Taylor polynomial. And no, they will not ask you to simplify this. They're not going to ask you to multiply x minus 1 to the 4th power, because that would be sheer madness. But let me take you through our simplified version here. And notice, this is as much as they're going to ask you to do. Negative 1 over 2 factorial is 1/2. 2 over 3 factorial, remember 3 factorial is 6, so 2 6 1/3. But they're not going to ask us to FOIL this out. So this is my 4th degree polynomial that's going to approximate my natural log of x. Okay, so when I look at the natural log of x, That's this guy right here. So there's my natural log of x. Okay. Now, this guy right here is my first degree Taylor polynomial approximation. Notice they have this point in common. Notice they have a little bit extra outside that where they match up. Okay, that's pretty good. My second degree polynomial, notice we have that same increasing through here. This guy's concave down, this approximation's concave down. Notice we have more in common. Okay. If we look at the third degree, we're picking up more. And the fourth degree, and this is what we actually found, if we were to put our answer in the calculator, this is what we would get. Look at this. We've got a lot in common. Think about if we took it to the fifth degree, we would have even more in common, sixth, seventh, eighth. The more degrees, the more derivatives, the more accurate we are, farther away from the point. Okay, and you would want to be farther away from that point. You want that accuracy because that allows you to make predictions. Okay, so if you're looking at an equation centered at x equals 1, you don't want to make a prediction when x is equal to 30 using this function because, wow, we are going to be nowhere close to it. So we want an equation that's going to be more accurate so we can make predictions about those. All right, so let's try one on our own. Oh, mercy, look at that. Sixth degree Maclaurin polynomial, okay? So Maclaurin polynomial, that means we're doing it at x equals 0, which means your c is 0. Well, sixth degree means I need 6 derivatives. Well, the nice part about back and forth. So let's do it. F of x is going to be sine. The derivative, this might be annoying, but we'll see what happens. The derivative of sine is cosine. Okay. The second derivative is going to be negative sine. The third derivative is going to be negative cosine. Okay, I'm going to go down to the next line because we're running out of room fast. Okay, the fourth derivative, we just keep going, so that's going to be sine. Okay, the next color, 5, is going to be cosine. Oh, weird. Look at that. We match up, How interesting. Okay, my sixth derivative, and hallelujah, my last one, negative sine. Okay, so I've got all of those values, all those derivatives. Well, now I need to know what that function is at 0. So let's see, what color have we not used? We've used them all. Okay, so let's see if we can't find some funky color. Let's do orange. Okay, so when I put 0 in here, when I put 0 in here, well, what's the sign of 0? The sign of 0 is 0. When I put the derivative into our cosine, I get 1. When I put 0 into the second derivative, I get 0. When I put 0 into the third derivative, I get negative 1. Okay, do the same thing here. 0. One, and of course 0. Okay. So now I'm ready to write my Maclaurin polynomial. I'm ready to change out of that tangerine color. So when I look at this guy, okay, remember your formula. Your formula starts off f of c, which is 0, plus my derivatives value at 0, which is 1, over 1 factorial, and then x minus c, which in this case is just x to the 1 power, plus my second derivative's value, which is 0, and I'm just going to write it out. I'll simplify it later. 2 factorial x minus c, x minus 0 to the second power, plus, now I'm going for the 3's, negative 1 over 3 factorial x to the third, plus, going to the value here, 0. Oh, that looks like a terrible 0. 0, 4 factorial x to the fourth. I'm squeezing it on, kids. You just wait and see. The fifth derivative at 0 is 1, so that's going to be 1 over 5 factorial x to the fifth plus, 0 over 6 factorial x to the sixth. Ooh, I told you I'd get that in there. All right, so now we've probably noticed that we've got a 0 term here. Well, 0 times anything is 0. 0 times anything is 0. 0 times anything is 0. So notice all of those even terms canceled out. 2, 4, 6, 8, 10, 12. As far as we want to go, those are going to cancel out. Okay, so what we end up with for our 6th degree polynomial, 1 divided by 1 factorial is 1. So x to the 1 power minus 1 over 3 factorial. Okay, and you can leave it 3 factorial if you want to, or you can change it into 6. Does not matter to me. And then plus 1 over 5 factorial x to the fifth. Okay, so even though it's a 6th degree polynomial, it ends at x to the fifth because that 6th term did cancel out. Now that you look at this pattern, if you just remember that for sine here, your polynomial x minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the fifth, you can go right to that. Now just to let you know, they do tend to favor sine of x, cosine of x, natural log of x, e to the x. Those are the polynomials that you're going to see over and over again that they will be approximating. So it's going to be to our advantage if we go ahead and memorize them. And I'll give you a list in class. All right, I'll see you back in class for day 1 of Taylor and Maclaurin polynomials.